All right, let's dive into one of those classic questions, one we've all asked that has a surprisingly beautiful scientific answer. It's one of the first things we ever wonder about the world, and today we're going to unpack the science behind it. I mean, come on, we've all done it. You look up at that massive blue dome over our heads and just think, why blue? Why isn't it green or yellow or just black like space? It feels like it should be a simple question, but the answer is anything but. The secret is all about the incredible journeys sunlight takes. It travels 93 million miles through empty space, and then, in just the last few miles, it hits the air above our heads. And it's in that final little stretch where everything changes. So first things first, we gotta unpack what sunlight even is. To us, it just looks, white or kind of yellowish, but that's not the whole story at all. It's actually hiding a secret rainbow inside. This secret was famously revealed by Isaac Newton in a classic experiment. He showed that when you shine a beam of white light through a glass prism, the light bends. But here's the crucial part. Each color that's hiding inside that white light bends by a slightly different amount, and that's what fans them out for us to see. And that beautiful band of colors that comes out the other side, it has a name. It's called a spectrum. This simple observation clued Newton in that sunlight isn't just one single thing. It's a mix of a whole bunch of different things. And what is it a mix of? Yep, all these colors, the classic rainbow. From violet and blue on one end, all the way to orange and red on the other. And here's the kicker. It turns out each of these colors travels in its own unique way, and that is the absolute key to this whole puzzle. Okay, so here's the big difference between them. Think of light as waves in an ocean. Blue and violet light are like these short, tight, choppy waves. Red light, on the other hand, travels in these long, lazy, rolling waves. This difference in wavelength is why the prism works. It just bends those short blue waves a lot more than it bends the long red ones. All right, so we've got our light figured out. Now let's move on to the second piece of the puzzle, the stage for this whole light show, our atmosphere itself. Because that beam of sunlight has to pass through something before it reaches our eyes. You know, the air we breathe, it's not empty at all. It's actually jam-packed with tiny, invisible things. Dust, water droplets, and most importantly, molecules of gases like nitrogen and oxygen. And the really crucial detail here is that these particles are incredibly small, even smaller than the waves of light trying to squeeze past them. Okay, this is it. This is where the magic happens. When that beam of sunlight, with all its different colored waves, finally slams into these tiny air molecules, they interact. A process called scattering happens. Yeah, scattering is pretty much exactly what it sounds like. The air molecules act like tiny little obstacles, knocking the light waves off their straight path and sending them bouncing in all different directions. It's kind of like a chaotic reflection, happening everywhere at once. But, and this is the most important part of this whole thing, it's not a fair fight. Those tiny molecules of air don't scatter all the colors of light in the same way. Well, they're kind of picky. See, those air molecules are just the right size to get in the way of those short, choppy wavelengths of blue light, so they scatter blue light like crazy. But the long, stretched-out wavelengths of red light, they tend to just roll right on over these tiny molecules without being bothered nearly as much. So let's connect all the dots. Let's see how this actually paints our sky blue. We've got sunlight with all its colors, and we've got our atmosphere full of tiny little particles ready to scatter it. Okay, so first, that beam of white sunlight, packed with all the colors of the rainbow, starts its plunge down through our atmosphere toward the ground. And as it's traveling, the blue part of that light starts bumping into air molecules and just gets scattered. It's thrown all over the place, while the red, orange, and yellow light continues on a much straighter path down. And we're not just talking about a one-time bounce. It's like a chain reaction. The blue light bounces from one molecule to the next, filling up the whole sky. The entire atmosphere just starts to glow blue. And that is the final piece. When you're standing on the ground looking up anywhere in the sky, you're not looking directly at the sun. You're seeing all of that scattered blue light coming at your eyes from every single direction at once. That's what our brain perceives as a big, beautiful blue sky. But what's really cool is that this same exact science explains why we get those incredible red and orange sunsets. It's not a different phenomenon, it's just a different perspective on the same one.
So think about it. At noon, the sun is right overhead. Its light is taking the shortest possible trip through the atmosphere to get to you. But at sunset, the sun's way down on the horizon. That light has to travel through way, way more air to reach your eyes.
And on that extra long journey, almost all of the short wavelength blue light gets scattered away from your line of sight. So what's left? What makes it all the way through to you? Only the longer wavelengths, the reds, the oranges, and the yellows. This is actually why danger signals are red. It's the color that scatters the least, so you can see it from the farthest away, even in fog or smoke.
Okay, to really nail this down, let's just flip our whole point of view for a second.
Let's finish with this question. What does an astronaut see? When they're up in space, high above all that air, what color is the sky to them? The answer, it's black, pitch black. Without that blanket of air, there's nothing to scatter the sunlight. It just travels in a straight line, and the sky looks dark. So our beautiful blue sky isn't a property of light or a property of space. It's a property of home. It's a constant, beautiful reminder of the very air that keeps us alive. It really makes you think, doesn't it? What colors might the skies be on planets with totally different atmospheres?